Okay, hello and welcome back to a new season of Midterms in a Pod. So today we're going to be talking about organic chemistry. Last semester, if I remember correctly, we did have an organic chemistry podcast, but it was for finals. But this time it's going to be midterm focused. And we asked our wonderful Professor Stephanie Abraham, Professor Stephanie Abraham, to help us out with this podcast. I'm the first interviewee, Melissa. I don't think that's really important. We can cut that out. Second interviewee. Do you want to introduce yourself too, or?
Yeah, so hello, I'm Linda. This is a collab between Addendum and Study Sheet. I guess we can start with questions.
Sure.
Thank you for agreeing to this podcast.
Thanks for having me.
So the first one is, what is the difference between an isomer, a constitutional isomer, and a stereoisomer?
So isomer is straight up just a blanket term for any two molecules that have overall the same molecular formula, but they're somehow different. And they can be different in a couple of different ways. One way they can be different is the constitutional isomer, which has the same number of each atom, but they're connected in a different order. So for example, you could have a chain of carbon, carbon, oxygen, carbon. That would be different from a chain of carbon, 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 and then ending with oxygen. So because they're connected in a different order, that gives us the different connectivity. Then we get into stereoisomers, which have the same connectivity, but then if you look at the molecules in 3D, they have a different spatial arrangement. So the atoms are connected the same way, but organized differently in 3D space.
My next question is, what are non-equivalent resonance structures?
So resonance exists in a bunch of different forms, right? You have multiple resonance structures. That is a way of moving the charges through your structure. I guess the best way to talk about non-equivalence is to first talk about equivalence. So equivalent resonance structures happens when, even though you're moving electrons through the molecule, the overall structure still bears all the same characteristics. So the same number of single and double bonds connecting the same types of atoms together, for example. So a non-equivalent resonance would be where those types of bonds and the atoms involved in them change. So for example, if you have, say, a double bond between carbon and carbon, and then a single bond between carbon and oxygen, and your next resonance structure has a single bond between carbon and carbon, and now a double bond between carbon and oxygen, it's different atoms involved in the single and double bonds, and therefore they are not equivalent with each other.
Thank you. And my next question is, what is a meso compound and how do we recognize one?
Meso compounds are a really special class of stereoisomer because they are not chiral, and every other stereoisomer is. They're not chiral because even though they have multiple stereocenters, they do not rotate plane polar isolates, and they have a plane of symmetry within the molecule. So meso compounds will have two or more stereocenters. So they do have the stereocenters, but because you can draw a line of symmetry right down the middle of the molecule, whether it's horizontal, vertical, whatever plane you use, if there exists a plane of symmetry in the molecule, it will overall be a meso compound. And you can prove this by drawing the molecule, drawing its mirror image, and you will see that they are superimposable with each other, which isn't supposed to happen technically speaking, right? So it doesn't have an enantiomer in that sense.
All right. What's the IHD and how do you calculate it?
IHD is the index of hydrogen deficiency, and what it does is it tells you how many degrees of unsaturation there are in a molecule, in a hydrocarbon specifically. So this tends to happen because if you have only carbon-carbon single bonds and carbon-hydrogen single bonds and stuff like that, then you have a saturated molecule. You'll have the maximum number possible of bonds to hydrogen involved. When you suddenly introduce a double bond, that uses up bonds that you could have used for hydrogens instead. So, and the same thing happens if you have, say, a ring. So essentially, every time you have a pi bond or a ring, you're introducing a degree of unsaturation into a molecule. So the IHD is going to tell you how many of those total you have in your molecule. You calculate it by taking the maximum number of hydrogens possible in your molecule. You find this by looking at the molecular formula. So for n carbons, the maximum number of hydrogens is 2n plus 2. So you take that maximum number and you subtract the actual number that's actually in the formula, divide that number by 2, and that is your IHD.
Thank you. So my next question is, what is the difference between a stereogenic center and a stereocenter?
They are the same thing. So there are multiple ways of identifying these species. Stereogenic center is one way of saying it. Stereocenter is another. Chirality center or chiral center, they all mean the same thing, and that's when you have a carbon bonded to 4 different groups.
My next question is, what's a functional group?
A functional group is essentially an arrangement of atoms that we assign specific general names to because they share similar properties. So, for example, if you have only a chain of carbon-carbon single bonds and carbon-hydrogen single bonds, that belongs to the functional group that we call an alkane. Whereas if you suddenly added an OH group attached to one of your carbons, that OH group suddenly turns that into an alcohol. So when you have a carbon connected to an OH group, you now have what we call an alcohol functional group at that part of the molecule. And every different functional group has slightly different properties in terms of physical properties, so melting point, boiling point, that kind of thing, and differences in polarity, depending on the electronegativity of the atoms involved in that group, and therefore that can then influence the reactivity as well.
I just wanted to add to that question. So it's probably important for students to remember the most common functional group.
Yes, exactly. So you all have probably been given your own version of a list of functional groups. And so the key is to recognize the general features for all of them. So like I had mentioned with the alcohol, right? If ever you see a chain of carbons and you see an OH group sticking out of one of them, you should be able to look at that and say, okay, that's an alcohol.
Perfect.
My next question is, what is the difference between steric hindrance and torsional strain?
Torsional strain is very specific to rotations of molecules. So when you have molecules engaging in free rotation, which all acyclic molecules do, essentially, as they rotate, there will be groups or substituents that get close to each other and then maybe get further away. So that connection, that moment of crossing each other, introduces what we call torsional strain. It is very similar to steric strain, but not quite the same thing. Steric strain is something that will just always exist. And so steric strain is not dependent on rotation to get there. It's just in a particular conformation, it exists. And it is basically when you have 2 different groups in your molecule that are close to each other, and therefore, even though they're not bonded to each other, they're still filled with electrons, as molecules or atoms, have electrons, and they will repel each other just because they are too close to each other, essentially.
There might be a question related to this, but am I wrong? By torsional strain, that involves going to be the Newman projection?
That's exactly it. So we saw torsional strain when we looked at Newman projections because we are seeing the rotation about a bond. And so we saw the eclipsed interactions versus the staggered. And so as you get closer to an eclipsed interaction, you're introducing torsional strain. And as you move away from it, you alleviate that strain.
Okay. I'm next, right? So yes. Can you walk us through the ARIO method and, if possible, tell us what it's useful for?
Yeah, absolutely. ARIO is a method of determining acid-base strength and relative acid-base strength based solely on the chemical structure. So you don't need a pKa table. You don't need any numerical quantified information. You just need to look at the structure, and then you can evaluate your acid-base strength. Typically how it works is we try to look at what the conjugate base of our acid in question is. So we take our acid in question, we magically pretend we deprotonate it for a moment and just do like a hypothetical situation, and we look at the structure of the conjugate base. ARIO is then an acronym of what you want to consider in determining the relative strength of that base. So A stands for atom, R for resonance, I for induction, and O for orbital. So first up is atom. So you want to look at the atom that lost the proton. First thing is, does that atom now have a charge? If that atom has a charge, then it is probably going to be a little less stable than something that does have a charge. So that's something that we're looking at. And then if it does have a charge and we're comparing different atoms, there are certain periodic trends that we use to determine which atom is better at holding a charge. Essentially, it goes in terms of negativity from left to right on the periodic table. So from left to right on the periodic table, electronegativity increases. The more electronegative you are, the more likely you are to want to have a negative charge, and then the more stable you are when you have that negative charge. So fluorine can stabilize a negative charge better than, say, carbon. Going down the periodic table, you are increasing in size. As your atom gets larger, there is more space to host a charge, and the charge can therefore be dispersed more, so it doesn't feel like it's concentrated all in one place, and that is also very stabilizing. So the lower you are in the periodic table, the better in that case too. Next up is resonance. So now you want to look at your conjugate base. Does your conjugate base benefit from resonance stabilization? Resonance essentially allows you to move the charge around because resonance moves the electrons around. And in doing so, you are doing what we call delocalizing the charge. So that is causing the charge to be dispersed and therefore less apparent, and that stabilizes the molecule. Next thing that we look at is induction. Induction typically happens in the presence of halogens. When you have halogens elsewhere in the molecule, so not the atom that just lost the proton, but elsewhere in the molecule, there is possibly a halogen. Halogens are very electron withdrawing because they are electronegative. So they want to attract electron density towards themselves. So if there is a negative charge elsewhere in the molecule, they will pull that charge towards themselves and help disperse the charge a little bit. It's not as acute of an effect as what you would see in resonance because it's not actually moving the charge over, but it is allowing a little bit of a trickle down effect there. Finally, we look at orbitals, and essentially we look at the orbital of the atom that has lost the proton, and there is a hierarchy here. So essentially, the closer to an s orbital you are, the lower in energy you are, and therefore the more stable you are. So an sp orbital is more stable than sp2, which is more stable than sp3, because those sp3, for example, has 3 p orbitals involved in the hybridization, whereas sp only has 1. And so essentially you can go through ARIO and figure out where you have a tiebreaker in terms of stabilizing your conjugate base. The more stable your conjugate base, the more acidic the proton will be, because there is an inverse relationship between acid-base strength. So when you have a very strong acid, your conjugate base is very weak, and weak in this case is synonymous with stability.
Okay, I just wanted to add another question regarding ARIO. I remember an assignment that we had to do in Organic Chem, and I remember that like going through ARIO, you cannot skip the steps, right? You can't go from looking at the atoms and go directly looking at the orbitals. Like that's not allowed, right? So
typically speaking, ARIO functions off of that hierarchy of going through A, R, I, then O. There can sometimes be exceptions. So it's not a foolproof method, but it's definitely generally going to work. And if there is an instance where it doesn't work, then you won't need to worry about that, because if you're taught to use ARIO, then that will be taken into account essentially.
Oh, great. My next question is, do you have any advice to remember all the trivial names?
That's a good question. So this is, just for clarification, are you thinking about some in terms of nomenclature also kind of thing, or?
Yes.
Well, so I guess for nomenclature, we'll say, right, common names, typically speaking, you're not going to be tested on those. because typically what we do, and this might vary from one teacher to another, but most of us prefer to test our students on the IUPAC names because we teach you all these rules. So it's the IUPAC names that we ask you to know. But within the IUPAC names, there are some weird ones, right? There's isopropyl, isobutyl, sec-butyl, tert-butyl. There's all the butyl ones. There's a lot of those, right? And so I have a few little tricks that I kind of use. So, for example, sec-butyl, if you look at the entire functional group or you look at that entire substituent, it is a chain of 4 carbons in a row, but they are attached to the main chain via the second carbon. So sec-butyl, second butyl is kind of how I think of that. And tert-butyl, for example, is a group where you have your carbon that's attached to the main chain. It branches out into 3 groups. So tert for tertiary in that kind of sense. So I have little tricks there to kind of remember them. But some of it is definitely more memorization. And I'm at a point also, and I realize this also makes me a little different possibly from you guys because I've been doing this a long time. So a lot of it is just in my head now, just from the sheer repetition of it, of how often I've done it. And that is honestly, that's not even a bad way to learn things, because the more you do something, the more it sticks in your head. And so that's always a good method, but when you have little tricks, it can definitely be more helpful. Other than that, in terms of other things that you might need to memorize, like functional group names, some of them are simpler than others. And I try to look for similarities, I guess. So for example, ether and ester are very similar. And so ether, it has a carbon-oxygen-carbon connection, whereas an ester is also that, but with a carbonyl as well. And so I consider, if I think about saying the names, ester versus ether, ester seems like a harsher name and ether seems more like a gentle name. And ester is what has the most in it. It has the most stuff. So that kind of is how I, compare and contrast the two. And then same thing with amine and amide. So amide has the carbonyl as well as the nitrogen group, whereas amine just has the nitrogen group. And I consider amide, again, to be a harsher word than amine. It's just because of the sound, and N is kind of softer than a D sound. Oh, okay. So it's little phonetic tricks, I guess, to kind of help with some of those. But it definitely gets easier the more you get familiar with them and the more you see them. And then there's some that are just giveaways of what they are. So haloalkane, for example, or alkyl halide. If you know what a halogen is, then it's an alkane group with a halogen, right? So some of them are more straightforward than others.
Thank you. That's really good advice.
Yeah, no, I never thought of the phonetic part. Yeah, no, that's smart. I mean, this is kind of similar to the previous question, and if you haven't answered it, well, I guess we can answer it. Mm-hmm. But in nomenclature, what is the general order of the name? So we're talking about the parent name, the suffix, etc.
So that kind of works in well that we were just talking about functional groups, I guess, because the idea is when you're doing nomenclature, it always has a prefix, a parent name, and then a suffix. The prefix is usually can be the most complex, I guess we should say, but the parent name and the suffix are really easily set when you have a structure. So the parent name comes from the name you would use depending on the number of carbons in your main chain. So if you have 1 carbon in your main chain, you use meth. 2 carbons in your main chain, you use eth, and so on and so forth. And we have that, all the way up to 10, and it goes even higher. It goes like to 100 and more than that too. Okay. So there you can have crazy carbon chains, but we're not going that far in this course. And then you attach the parent name to the suffix. And that's really one of the first things you can do when you're putting a name together, is attach the parent name and the suffix together, because that will tell you how many carbons in your main chain and what is the main functional group you're working with. In most cases, or in a lot of cases, you may be just starting with an alkane, so then your name will end with ane. So it's the parent name and then ane. So methane, ethane, propane, and so on. If you have an alkene, then the name ending becomes ene. So ethene, propene, butene. If you have an alkyne, you change the ending to -ine. So ethine, propyne, butyne, and so on. And then finally, other ones that we look at are alcohols. And if you have an alcohol, it can be like methanol, ethanol, propanol, and so the ending changes depending. So that's the parent name and the suffix. Gives you the number of carbons and the main functional group involved. The prefix can get complicated because you might have substituents. So from your main chain, you might have all sorts of substituents attached to that chain. So that's the next part that you want to build. And so we have rules for how do we number our main chain. And typically we want to number it in a certain direction that will allow us to have substituents with the lowest possible numbers. And so we have to number where all of our functional groups are, where all of our substituents are, and we put that all together in a prefix at the very start of the name. And then, last thing, if we want to get even more complicated, maybe we have stereochemistry to consider. And that will go at the very front before the prefix, and that will put the whole name together.
Stereochemistry is like the RS configuration.
RS and cis-trans.
Cis-trans, okay.
Yes.
Like another note to add to this, I feel like it's strange, but I feel like we've only worked with like the ane, so methane, alkane. Like
So-
we just worked with alkanes basically.
So it depends also who your professor is. So you're going to learn all of these. Whether you have yet or not depends on who's teaching you and what order they teach in. But the different suffixes that we see in this course primarily are alkanes, alkenes, alkynes, and alcohols.
Okay.
Okay, thank you. And the next question is, how can one determine relative acid and base strength? And I guess this one is based on pKa, since you already explained using ARIO.
Yeah, I already explained using ARIO, so I won't say that one again. But if you do have pKa's instead, then that is more or less straightforward because you have the numerical justification right there in front of you. If you're comparing two bases, then look at their conjugate acids. So add a proton to wherever your charge would have been, and essentially look at the conjugate acid pKa. The lower the pKa value, the smaller the pKa value, or the more negative the pKa value, the stronger the acid will be. Therefore, the conjugate base will be weaker. Acid-base strength is always that inverse relationship. So whichever acid is your weaker acid, then its conjugate base will be the stronger one between the two, and that's how you do those comparisons.
Okay. Yeah, no, that's kind of messing up my mind right now, so I'll take that into account next time. Okay, well, this is like somewhat a series of questions because it's all related to pretty much chair flip formation.
Mm-hmm.
And I'm just gonna add a little warning here, I guess. The chair flip formation is very much a visual thing. It's much more helpful to see it visually, but Professor Abraham will do her best to verbally explain it, but visual is always better than...
Yeah, so what we suggest is you take out a pen and a paper and try to draw out the conformation as the professor explains.
Yes. Alright. Okay, let's start. There's how many questions in total? 5 questions in total that's related to this, I think. So, first one being, what's the difference between an up and a down C?
Okay, so every time you have a chair conformation, essentially what makes the chair a chair is that it allows all of our carbons, which are all sp3 hybridized, to maintain the geometry that they want to have, which is that tetrahedral shape. If you have a model kit, for example, you could try this out with a model kit and make a ring of 6 carbons. If you tried to orient that ring so that it was perfectly flat, the angles would all be off. And you would feel the model strain in your hands because it wants to bend into a different shape. So the proper shape of a chair is kind of like a circular zigzag, where you alternate carbons pointing up, down, up, down, up, down, and so on. So if you consider it as if it's an acyclic alkane and just a regular chain, we can kind of see in the zigzag that carbons are pointing up, then down, then up, then down, and so on. It's the exact same thing in a chair. So the carbons that seem to point up, those are your up carbons, and the ones that are more downwards are your down carbons. And so it always alternates up, down within the chair.
That's good, thank you. What's the difference between axial and equatorial?
Okay, so you always have outside of the ring 2 other substituents because every carbon can have 4 bonds max. It has 1 on each side of the ring and then the 2 extras. So the 2 extras will always have 1 pointing axial and 1 pointing equatorial. Axial is going to be vertical. It's either going to be vertical up or vertical down. This depends on what carbon it is attached to. So a carbon pointing up, again from our zigzag of up-downs, all of the up carbons will have axial pointing vertically upwards, and all of the down carbons will have axial pointing vertically downwards. So each of those carbons will have an axial. They also need to have an equatorial. Equatorial is more or less horizontal. It's not quite perfectly horizontal. They're on slight angles, but they will point more horizontally for sure compared to, say, the axial bonds. So every carbon, again, will have an equatorial, and this will point in the opposite direction of the axial. So if you have an axial up substituent, then your next bond will point equatorial down. If you have axial down, your equatorial will point slightly upwards.
All right, next question is, how do you determine the stability of a structure from its chair form and ring flip?
Okay, so what we do when we analyze our conformations of cyclohexane, the most stable conformation of cyclohexane by far is the chair form. However, this chair can exist in two conformations, the original chair and then the ring flip. So when we want to evaluate which of the two now is more stable, we have to perform that ring flip. So you start off by just drawing your first chair form, and then you convert it to the second via the ring flip. And then you want to evaluate your substituents and where they are located in both versions of the chair. So we're looking at axial versus equatorial. The more groups you have in the axial position, the less stable your molecule will be, because that gives rise to diaxial interactions, which give us steric hindrance that we mentioned earlier. That's when bigger groups are coming too close to each other. So they will inherently want to repel each other because they're too close to each other. So the more groups you have in the equatorial position, the better. And if you have larger groups, so some substituents are larger than others, you want the bigger ones. You prefer for the bigger ones to be in the equatorial position because that has more space and that minimizes your steric interactions.
Now we're on to Newman projections.
So staggered and eclipsed are the two main types of conformations that we have in a Newman projection. That is the rotation about one single bond in an acyclic molecule. We typically see this. And essentially staggered is when you look down a Newman projection, you can see all of the different groups all at different angles from each other. So if a Newman projection is nice and circular, essentially at 0 degrees, 60 degrees, 120, 180, 240, 300, back to 360, you see something at each of those angles. When you have an eclipsed conformation, the groups in the front are blocking the groups in the back. They are directly in line with each other. And so it only looks as if you can see 3 different positions rather than all 6 going around your projection.
The question here says, how do you differentiate anti from gauche conformations, especially when there are 3 CH groups, 2 in the front and 1 in the back? I think this refers to like the assignment that we had.
Yeah, so I think this is referring specifically to assignments. If you had me as your professor, then you had this question on your assignment. I don't know about other professors' assignments, but essentially an anti-conformation is when 2 groups, specifically the 2 biggest groups on either carbon involved looking down the bond, are 180 degrees from each other. Gauche is when they are only 60 degrees from each other. So you can have, technically, if you have 3 substituents, 1 on one carbon and 2 on the other, and they're all the same size, then you can have a combination of gauche and anti interactions. And essentially, because there's no way to put 3 groups 180 from each other, only 2 groups can ever be a complete 180 from each other at a time. But as long as that's there, you have an anti-conformation because you've fulfilled the definition of the 2 biggest groups being 180 degrees from each other.
So in a sense, the moment there's anti, it trumps the gauche conformations.
Anti does trump the gauche conformation in the sense that when you compare your different staggered conformations, it will change things energetically. So if we're talking about, I know the question was alluding to my specific assignment question, so those of you who didn't have this question, I apologize for the maybe lack of clarity here. But essentially, if you have all 3 substituents all gauche to each other, that's very different from having two of them gauche to each other and then the other relationship being anti, because anti is much further away than gauche, so anti will lower the energy and increase the stability of that conformation compared to only having gauche interactions.
And just to add on a quick question, so are we always comparing two large groups on the two different carbons and not two large groups on one carbon?
Exactly, because you cannot physically get gauche or anti interactions if they're on the same carbon, because you cannot get because if you look at a Newman projection, a gauche interaction is when the groups are 60 degrees from each other. But within one carbon, which is tetrahedral, you are 109.5 degrees from each other at all times. So you can't get a 60-degree interaction there. You can't get a 180-degree interaction there. So it's very specifically the biggest group on each of the two carbons you're observing. So the one in the front and one in the back.
Okay, that's all for my 5 very visual questions. And another reminder, these are very visual questions, so take out a piece of paper and try to draw it out as you listen.
Alright, we can move on to the next question. So, how can we show that two molecules are a pair of enantiomers?
Okay, so the best way to prove that you have a pair of enantiomers, in my opinion, is to try to line them up as best as you can. So whatever is in 2D, typically your carbon chain, try to mimic everything and try to make the molecule and draw it out in such a way that you could try to superimpose one on top of the other. If you can take the carbon chain and fit it perfectly on top of the other, you'll then see that you have an enantiomer specifically at your stereocenter, or stereocenters if you have more than one. Essentially, the enantiomer will have the carbon chain, or the main chain, perfectly line up, but at every single stereocenter, front and back will be reversed. So that's what you're kind of looking for when you're looking for an enantiomer. There are other ways. That's, again, what I said is subjective. That's the preferred way that I have to do it. Another way is, can you prove that these two structures are mirror images of each other? And also non-superimposable, that would be the other key.
Alright, thank you.
Okay, my question is, what's the difference between cis and trans?
So cis and trans are ways of describing the relationship of two substituents to each other. Typically, you will see this in rings. You can also see this in alkenes. If you're in my class, we haven't seen that yet, but we will be eventually. But essentially, cis means the two groups are pointing on the same side. So phonetically, cis, same side, is all the S sounds, and that's kind of how I remember it. And trans is when the two groups are pointing on opposite sides. So when you have, say, a ring, for example, like a cyclohexane, if you have a cis relationship, you have two substituents either both pointing up or both pointing down. And if you have a trans relationship, one substituent is pointing up and one is pointing down.
Thank you. My next question is, what are the conditions for an isomer to be considered a diastereomer?
Yes. So diastereomers they're kind of funky in that diastereomers is a dump term almost in a sense, because we have all these different specific definitions for all our other kinds of isomers. Right, so constitutional isomers, we know the connectivity is different. And then within stereoisomers, we have enantiomers, and then we have diastereomers. So within stereoisomers, it's molecules that have the same connectivity, but overall have some sort of different 3D spatial arrangement. And enantiomers is very easy. Enantiomers, it's non-superimposable mirror images. But not everything is necessarily a mirror image of each other. So when you have the same connectivity but different 3D arrangements and it doesn't fit into the definition of an enantiomer, we call it a diastereomer.
Thank you for clarifying that.
My next question is, what is R and S and how does it fit in nomenclature?
So like we were talking before, when we have, enantiomers, for example, we have non-superimposable mirror images. And essentially that means at any stereocenter in the molecule, they are pointing in the opposite, the groups are pointing in the opposite direction. So the problem with having this is, how do you know which enantiomer you're talking about when we're talking about them? So when we have a stereocenter, there are only two possible ways the four groups can be oriented before you start getting duplicates. So we have two possible ways to orient them. So two possible ways to name them, essentially. And that's where the RS system comes into play. So one way, and we have a system, I guess you could say, and a set of rules to allow us to determine whether a stereocenter qualifies as R or S. And so whenever you have a pair of enantiomers, one will have the R stereocenter and one will have the S. And you can then use that to distinguish which one you have based on your rules for designation. And RS designations will then go to the very front of your name when you're doing nomenclature. So I mentioned this earlier where the very, very front of your nomenclature is where you would put RS or cis and trans and that kind of thing. So that's where you would designate your RS, and that way when you write out a name, you know which stereoisomer you're talking about. Essentially, the rules for determining RS is you want to look at all the atoms directly attached to your stereocenter and order them in terms of priority. And then we have tiebreaker rules to help determine if there's a tie, because you branch out and keep going until you have a tiebreaker. And essentially, once you've determined all your priorities, you want your lowest priority group, so priority 4, to be in the back. Trace a circle from priority 1 to 2 to 3, ignore 4. And if the circle is clockwise, then you have the R designation. And if the circle is counterclockwise, you have the S designation. This only works when the lowest priority group is in the back. If your lowest priority group is in the front, then whatever you find, it's actually the opposite. And if your lowest priority group is in the plane of the page, you have to rotate your viewpoint to get it into the back, otherwise it won't work.
All right, perfect.
Cool. So I'll ask my next question. Do you have any tricks or a systematic way of finding all the possible structures of a molecule simply from a molecular formula?
Okay, this is a fun one. So yeah, there are a few tricks that I use. But at a certain point, it depends also on the complexity of the formula. The more carbons you have, the more potential for structures you have. And this number can increase exponentially. It can get really, really, really large. So once you start getting, past 5, 6, 7 carbons, it's near impossible, probably in a feasible amount of time, to actually figure out everything you can possibly have. And when you start introducing extra functional groups, if you add extra atoms like nitrogens or oxygens or halogens, that makes it even more complex. But what I like to do is I like to first determine the IHD, and the IHD will tell me if I have degrees of unsaturation. If I have any unsaturation, then I can guess at what kind of functional groups I might have. For example, if I have 1 degree of unsaturation, my molecule could have a ring. It could also have a pi bond. So what I would then do is take my number, whatever my max number of carbons is, and make a chain with that maximum number and alternate where I put the pi bond in that chain. Or if I make a ring, I'll alternate where I put the pi bond in the ring. And then I will shrink the chain and add substituents, or shrink the ring and add substituents, and then again change where I put the pi bond and that kind of thing. So it's so either I have the 1 ring or I have the 1 pi bond, and the pi bond moves through the chain, or the ring size shrinks, and then I have other substituents. And I kind of play around that way, slowly shrinking and adding substituents as I go.
But I believe that during an exam, you wouldn't ask us to draw every possible structures.
It can be, yeah, because one example that I do in my lectures, if you have me as your professor, I like to do C7H16, and there are 9 possible constitutional isomers of that. And that's something that works very well for a class experiment, but when you're doing it on a test, that's a lot to ask of someone. So me personally, I wouldn't ask that level of complexity, or I would ask to give 2 or 3 only kind of thing. But for those of you who are not taught by me, I would always recommend you ask your own professors what they prefer. I don't expect they would give you something that complex, but everyone is a little bit different. So these are the kind of things that you always want to check in with your own professor for their discretion there.
All right, and adding in a quick question about it. So a way to avoid having drawn the same structure, the same molecule actually, but having flipped it by accident, it's just counting the longest carbon chain. Counting the longest carbon chain,
a trick that you now have that you maybe didn't have when we were first just playing around and drawing things, is find the IUPAC name. If you have the same IUPAC name, you have the same molecule. So all constitutional isomers have different IUPAC names, and that is a given. So you can always name them, and that would also tell you right away if you have the same thing.
My next question is, what do we have to understand from the energy diagram?
So for a Newman projection, essentially your staggered conformations are always lower in energy than your eclipsed. So because when you have eclipsing interactions, that's where we talked about torsional strain earlier. That introduces the most torsional strain as the groups are moving closest to each other. So you're going to have the highest energy there. Whereas staggered, all the groups are spaced further apart from each other. They have, I guess you could say, breathing space. So staggered is always lower in energy than eclipsed. But then within your staggered conformations and your eclipsed conformations, they might differ from each other, relatively speaking. So like we were talking about earlier with gauche versus anti, something with an anti-conformation will be lower in energy than a gauche conformation because the bigger groups are further away from each other. And then same thing with your eclipsing interactions. When you have big groups eclipsing each other, that is going to be higher in energy because that's introducing a lot more strain. So it's all going to be relative based on whatever your different conformations look like. And so you have to analyze it one molecule at a time, each different conformation, to see what the relative levels are going to be like.
And it's through that we can also determine which projection is the same energy level as
Exactly, because some of them will be exactly the same because they'll have the exact same amount of gauche interactions or eclipsing interactions, that kind of thing.
All right. So what is the arrow pushing mechanism?
So an arrow pushing mechanism is using arrows to show, or curved arrows specifically, to show where the electrons are moving in a reaction. So if a bond is being formed, typically the arrow will start on a pair of electrons, typically a lone pair, and the arrow will point to the atom that they want to attach to, and that will then kind of form a bond. If you are breaking a bond, you will start your arrow at the bond line between two atoms, and the arrow will point towards the atom that's taking the electrons for itself. And most chemical reactions are going to be a mix of that, of lone pairs or pi bonds reaching out and grabbing something, and other bonds breaking and atoms taking electrons back for themselves. And so an arrow pushing mechanism is basically showing how we get from our reactants to our products, showing the electrons moving, forming bonds, and breaking bonds in the requisite number of steps that they take.
So this is my last question. How is nomenclature for alcohols different?
So nomenclature of alcohols is a little different from, say, a regular alkane, for example, because it replaces the suffix. So if you had ethane, but now ethane has an OH group attached, it's no longer just ethane, it's ethanol. So we take away the E at the end of ane, and we add all at the end. There is a priority, I guess you could say, in terms of certain functional groups, whether they behave as substituents or whether they go into the suffix. And so alcohols go into the suffix, whereas halogens, for example, are just substituents. So that's kind of the difference there, and that's what makes alcohols different from them. And then when you are numbering your carbon chain, you want to give the alcohol the lowest possible number. And that trumps any other substituents that you might have.
All right, cool. Thank you. And my last question here, what is a ring strain?
Ring strain is a strain in cyclic molecules, specifically cyclic alkanes that we've seen the most of. And essentially that occurs when your bond angles are not 109.5. This happens especially, for example, in cyclopropane, the 3-carbon ring, because a 3-carbon ring is basically a triangle. If you're going to draw that out, it's an equilateral triangle, which means the bond angles within the ring are 60 degrees. But carbons are sp3 hybridized. Their bond angles are supposed to be 109.5. So that's a difference of 109.5 versus 60. That's a massive difference in angle. So that introduces a lot of ring strain because the bonds are very strained and they're very weak because of it. So any molecule that has bond angles of less or greater than 109.5 in a ring, it will always exhibit ring strain because of that. And that's why we have our molecules like cyclohexane. They don't exist as a flat structure. They exist in the chair form because that causes all the bond angles to fit the 109.5.
And I'm assuming that a ring strain is also makes them less stable in general.
Exactly.
Yeah.
It makes, when you have a lot of strain, any kind of strain, it will make the molecule less stable. And cyclopropane is a very unstable and reactive molecule because it has a lot of ring strain.
Okay, thank you so much for answering all our questions.
No problem. That was a lot of fun. Thank you for having me.
Thank you for listening to this episode of Midterms in a Pod. Don't forget to check out our other episodes on waves with Professor Binet. Of course, don't use this as your sole review material. Do your exercises, study, and you'll do great on your exams.
Yes. Last year, Addendum and Study Sheet already released a bunch of podcasts regarding midterms and finals. Use these as well to help you during these hard times. I hope this was helpful for you guys.
Yes. Thank you for listening and good luck on your exams.